Okay, in the last video, we had derived this answer here for a solution to the integral of the hyperbolic cosecant of x. And it took us a couple of videos to get to there, but we eventually got this answer. And a couple of videos ago, we had derived this as an answer to the hyperbolic secant of x. Now, if you compare the two problems, what's interesting is when we express this problem here in terms of its exponentials, its basic definition, we were able to go ahead and eventually integrate it, but the answer we got did not look anything like this. So then what we did in another video was we used the identity that the hyperbolic secant squared of x is equal to 1 minus the hyperbolic tangent squared of x. And when we use this identity to say that the hyperbolic secant of x is the square root of this, and we put that square root inside the integral sign, we got this answer right away. In this case, we used the basic definition, and we got this answer here, which if you look it up in the table of integrals, is most likely this is what it's going to show to you. But there's also a hyperbolic identity here that comes into play, because the hyperbolic cosecant squared of x that's equal to the hyperbolic cotangent squared of x minus 1. So if we do now what we did with this problem, use its hyperbolic identity to rewrite the integral like this, the square root of hyperbolic cotangent squared of x minus 1 dx. If we look at this, that should remind us of an integral where the trig substitution might apply, because what we have here is a variable squared minus a constant, and the trig substitution that should remind you of is the secant squared of theta equals the tangent squared of theta minus 1. A variable squared minus a constant. Here we have a variable squared minus a constant. They're the same general format. So what we do is we say, let the hyperbolic cotangent of x let that be equal to the tangent of theta. That's our substitution. Now we put that substitution in here, we're going to have the tangent squared of theta minus 1. Well, that's the secant squared of theta, and we're taking the square root of it. So this part of the integral now becomes the secant of theta. What about dx? So now we have to take our differentials, and here we're going to have minus the hyperbolic cosecant squared of x will equal, and this will be the secant squared of that, or our theta, and we didn't write our dx here. We have minus the hyperbolic cosecant squared of x dx, that's the differential of the hyperbolic cotangent, and that would be equal to the secant squared of theta d theta. Now remember, from up here, the hyperbolic cosine squared, that's this, so we can rewrite this as minus the hyperbolic cotangent squared of x minus 1 dx. That's just using our hyperbolic identity again for the hyperbolic cosecant squared equals the secant squared of theta d theta. With the hyperbolic cotangent squared of x, that would be the tangent squared of theta. We made that substitution here. So over here we would have minus tangent squared of theta minus 1 times dx. Let's write this a little bit neater. Minus, this is the tangent squared of theta minus 1 times dx, and that's equal to the secant squared of theta d theta, with the tangent squared of theta minus 1, that is the secant squared of theta. So you divide both sides of the equation by this, and we're going to have dx, that's just going to be equal to minus d theta. So this integral here now becomes the integral of minus the secant of theta d theta. And the integral of the secant of theta, hopefully you recall, is the natural log of secant of theta plus the tangent of theta. And we have a minus sign here. Now we have to go back and remember our substitution. That was this right here. We said let the hyperbolic cotangent of x be equal to the tangent of theta. So we can express this in terms of the variable x. That's just the hyperbolic cotangent. But what about this? So again, we draw a triangle. We have that the hyperbolic cotangent of x equals the tangent of theta. So when we draw the triangle, and here's theta, the tangent of theta equals this divided by 1, and the tangent of theta equals the side opposite divided by the side adjacent. So the hypotenuse here is just going to be the square root of this squared plus 1. So now we go back to here and we can express our thetas into the variable x by using a triangle. So let's see, we have minus the natural log of the secant of theta. That's the hypotenuse divided by 1, so it's just going to be this. And the tangent of theta, that's just the hyperbolic cotangent of x. So this will be equal to here, the square root, the hyperbolic cotangent squared of x plus 1 plus the hyperbolic cotangent of x. This divided by 1 would be the secant of theta, and this divided by 1 would be the tangent of theta. So now what we're saying is that the integral of the hyperbolic secant of x dx equals minus the natural log of the square root of the hyperbolic cotangent squared of x plus 1 plus the hyperbolic cotangent of x plus an arbitrary constant. And obviously this answer here is entirely different than this answer here. And again, if you look up in integral tables, these here are the answers you're most likely to see. What we want to stress is that sometimes when you're trying to solve an integral and there's multiple approaches available to you, they might give you different expressions. Also, when you have multiple approaches available to you, if you're struggling with the integral and you can't get the answer, rather than giving up, try one of the other approaches. It might turn out to be considerably simpler. And we'll try to have some other videos that will try to illustrate that point, looking with some more problems.